Hello, welcome to the course Transducers for Instrumentation. Today we are going to discuss some characteristics of sensors. These characteristics are some parameters for which we develop the sensors. So, for example, in a particular sensor we have this much of resolution, this much of linearity, range. What are all the parameters for which a sensor is need to be designed? So, these are some characteristics of a sensor which we are going to discuss. So, in normal environment the data comes in and this data is not a pure data, it is full of noise and it keep changing. So, these sensors what we are going to design, these are required to be appropriately characterized. So, because the data is noisy, so we need to take care of this noise and the sensor need to filter out the data from it. So, the term here is this characterization. So, this characterization is done in terms of certain parameters and characteristics of sensor. So, there are certain parameters for which this sensor is need to be characterized, and these sensors are like measurement systems. They have two types of characteristics, one is the static and one is the dynamic. Before discussing these static and dynamic characteristics, we have a term in hand which is characterization. So, what is a characterization? So, the device characterization is the process of quantifying the electrical behavior and performance of electronic device. It may be another device, but we are particular about electronic systems. So, we are discussing electronic devices. So, this characterization is the process of quantifying, how we can quantify the behavior of a device such as transistors, diodes, sensors, etc. So, this involves measuring the various electrical parameters such as gain of an amplifier, stability and various other terms. This involves measurement of these electrical parameters and these frequency response. Repeated measurements, it allows engineers to understand how the device operates under different operating conditions, because the sensor is not going to work throughout its life at a particular fixed voltage or fixed parameter only. This parameter is going to be changed, and because of that the output of this sensor is going to be changed. So, we need to characterize this sensor so that we know upfront what is the input parameters, and based on that what output is going to be there. This is also done to know any performance limitations or issues with the sensor upfront. So, if we have, let us say, sensor has a limited range, so that can be quantified using characterization process. In characterization process, what generally we do, we apply a full range of input parameters and check the output of the sensor. So, this gives us the idea of how the sensor is going to perform in real world. So, this is called characterization. So, what we do, we characterize the sensors or transducers in terms of certain parameters, and these parameters or these characteristics are of two types. One is the static one and one is the dynamic one. So, as the name says, static characteristics, we have the characteristic of sensor which does not evolve or does not change with time. So, these characteristics are like sensor, the sensitivity. The sensitivity is something, how much is the change in the output for per unit change in the input. So, that is called sensitivity. Resolution, for example, the smallest amount of change in the input that can be detected by the sensor. So, that is called resolution. Linearity of the sensor, for example, how much the sensor output deviates from a standard state line output. Drift is one another property. So, there is a drift in the output of a sensor with the input. It kind of drifts from its regular output by a certain amount. So, that is called drifting, and there are special cases in that. There are some zero drift, full scale drift, there are other types of drift. Range, we characterize the sensor for range as well. Range is the upper limit minus the lower limit of the output or the input. Repeatability, this is also something does not change with time. So, if we apply a repeated input at the sensor, how much the output deviates from its previous input. So, we apply, let us say a similar input 10 times, all 10 times the output will not be same. There will be a certain difference at the output for all the 10 inputs. This is called the repeatability issue. So, the sensors has this repeatability issues. Reproducibility is another characteristic which is static characteristic. Repeatability over long time lapses between the measurements. So, these are some static characteristics which we are going to discuss in detail. The other sensor characteristics are dynamic in nature. Dynamic means the output of the sensor actually drifts or it changes with time. So, these are called dynamic characteristics. So, these are, first is rise time. So, for example, we have a sensor, when we apply a step input for example to this, and the output changes like this graph, it shoots up and then it goes down and it settles down to certain final value. So, there is a rise time involved. Rise time is how much time the output of a sensor takes in reaching from 10% of the final value to the 90% of the final value. So, for example, we have 1 which is kind of normalized output. So, 0.1, 0.1 to 0.9. So, this much and this much. So, this time difference what this sensor takes from reaching from 0.1 to 0.9, this is called the rise time of a sensor. Delay time is how much time the output takes from reaching from 0 to 50% of its final value or the steady state value. So, steady state value, as we have seen, this is 1. So, how much time the output takes from 0 to 50%, and here it is shown as TD. This is the delay time or the time delay of the sensor. The peak time is how much time the output takes starting from 0 and to reach the peak value of its output. So, peak value is this value which is MP here, and how much time the sensor takes is 0 to TP. So, TP is the peak time. This is the time it takes in reaching from 0 to the peak value. The settling time is the time taken by the output to reach its steady state value. Though this is the dynamic characteristic and it takes very long time in settling to exactly value of 1. So, we define a criteria that when the output reaches 1% or 5%, that depends on the application. So, when the time taken by the sensor to settle down to within 1% of the steady state value. So, this steady state value is 1%, and when the output reaches to 1% of this value, then we say this is the settling time, and typically we can see is plotted here Ts, which is typically 1% of the steady state value. The percentage overshoot is something how much the output overshoots above the steady state value. The steady state value is 1, and how much in percentage this output overshoots above this value of 1. So, this is again MP, the peak, this is TP, which is peak time, and in peak time the output approaches the percentage overshoot. So, this is the percentage overshoot, how much the output overshoots above the steady state value. Steady state error is deviation of the actual SSV from the desired value. So, how much the steady state value is different or is deviated from the desired value. These are the some dynamic characteristics. So, let us discuss these static characteristics first in detail. So, these are some of the static characteristics which does not change with time, and these depends mostly on the sensor, the quality of sensor, the material of the sensor, and these characteristics are inherent to the sensor. The first one is accuracy. So, the accuracy is specified by actually inaccuracy or usually error in the measurement, and the formula for error is given like this: epsilon A, which is the error in percentage, is equal to xm minus xt divided by xt into 100, where xm is the measured value and xt is the true value of the measurement. So, the error actually is how much is the difference between an actual value of a parameter and the measured value of a parameter. For example, we have a stick which is 1 meter in length. This is the actual value or the true value of this object, which is 1 meter, but when we measure it using a tape, we measure out to be like this is 101 centimeter or 1.01 meter. The actual value of the object is xt, which is 1 meter only, but xm, the measured value, is 1.01, and because of this measurement we have a error in measurement which is given by xm minus xt, which is 1.01 minus 1, minus 1 divided by 1. So, this is the error which we have in measurement, and we multiply it by hundreds so that it comes in percentage. So, this error is actually the difference between actual measurement and the measured value, and which is normalized to the true value of the measurement. So, this is called epsilon A. Sometime this error is often expressed for a full scale output as well. What we mean by this full scale output is, we have a sensor or a meter. This has a particular range, let us say from 0 to 100. So, this sensor is going to measure only from 0 to 100, which is the full scale or this sensor. So, we define this error as a full scale output, means how much is the error in percentage for a complete full scale reading. So, we define this by epsilon FSO is equal to xm minus xt, which is the measured value and the true value, but this is now divided by the full scale XFSO, which is the full scale output of the sensor, and we multiply again with 100 so that it is in percentage. So, this error is often expressed in terms of the full scale output. So, we have two ways of expressing this error, which is one, the accuracy as a percentage of full scale, percentage Fs, or percentage of reading, which is the first case where we normalize it with the true value of measurement. There are difference between these two expressions of errors. Let us take it using an example. If we have an instrument where the accuracy is specified as percentage Fs or the full scale, if we specify the error as a full scale output, then the error will have a fixed value no matter where the flow is in the flow range. So, here we are talking about a flow meter which is going to measure the flow of liquid, let us say water. So, this is the diagram of a flow meter where the liquid goes in, goes out, and this has a particular range from, let us say, 0 to 100 or something. If we show the error as a percentage of full scale, then the error will have a fixed value. We calculate this value at a full scale and this error remains fixed no matter how much liquid is flowing into this flow meter. So, for an example, this instrument calibrated for a flow of 100 liter per minute with a stated accuracy of 1% of full scale. It means when a flow of 100 liter is there through this sensor, the error will be 1%, 1% of 100 liter, which is 1 liter per minute. So, this error is now fixed because we are expressing this in terms of full scale. No matter now how much liquid is flowing into this sensor, the error is plus minus 1 liter per minute. This is the error which is produced by this flow meter. Now, if instead of 100 liter per minute, now my flow is only 50 liter per minute, but the error remains same, 1 liter per minute. How much is the error in percentage now? 1 liter in 50 liter per minute, which is 2%. This is now higher than 1% what we have shown for a full scale reading. Going further, if the flow reduce further to 10 liter per minute, this error remains same 1 liter per minute, then the error is 10%, which is quite huge error. So, if we express the error in terms of full scale reading, then the magnitude of error remains same, and if the input reduces or the output reduces, then this error becomes significant compared to the full scale output. However, if we express this error in terms of percentage of reading, then this always remains percentage of what actually the flow is. So, for example, if we express this error in terms of percentage RD, then 100 liter per minute has a percentage of 1%, it means 1 liter, but when the flow reduces to 10 liter, the error is only 1% of 10 liter. Which is quite less error compared to what we have shown in full scale case. So, these are the two ways of expressing the error as in terms of full scale output or in terms of the actual magnitude. The next static characteristics is precision. So, the precision is how far the measured quantity is reproducible, as also how close it to its true value. So, the next quantity is precision. So, the precision is up to how far the measured quantity is reproducible. So, we have output which is y as a percentage of full scale, and the input is x which is in percentage. Now, we sweep the input from 0 to xm, which is the complete value. If we do this same measurement multiple times, there is going to be the difference in the output. So, in one case when we sweep from 0 to xm, the output traverses this curve, let us say this is 1. If second time we apply the same input from 0 to xm, the output is this second graph. So, there is a certain difference between these two output, and this is called the repeatability. It means that the sensor is not perfectly repeatable, and there exists a certain change or the certain difference in the output for the same input. So, this term repeatability is close to precision, which is the difference in output at a given value of input when obtained in two consecutive measurements. Next, we come to the difference between accuracy and precision. What is the difference between an accuracy and a precision? Accuracy is the agreement between the measured value and the true value. It shows that what we measured, how much it is close to the true value of the object, true value of the parameter. However, the precision is, if we repeat the experiment multiple times, how closely the output is confined. All the output should be in a very close range, that is called precision. In a graph, if we plot, on the y axis we have this probability density function, and on the x axis we have this value, which is where we have this true value of output. This is the true value or the reference value. But when we apply multiple measurements, and most of the time we end up at this value, which is, let us say, our mean value of measurement, and the difference between this actual value or the reference value and this measure value, this is our accuracy. However, we are doing this measurement multiple times, and let us say all these 100, for example 100 measurements, all these measurements are lying here, follows a Gaussian curve, and the peak exists in between here. How confined these output are in a particular range, this is specified by the precision. So, this is the accuracy, how much is the difference between actual and measured, and how much output is confined to a narrow range, that is called the precision. So, accuracy indicates proximity to the true value, however, the precision to the repeatability or reproducibility of the measurement. This is the difference between the accuracy and precision. Accuracy is the degree to which the measured value is close to the correct value. Measured value is close to the correct value. However, the precision is, it describes how close the measured values are to each other in the data set. It need not to be the accurate one, or it need not to be close to the true value. Usually accuracy involves single factor measurement. You just apply one input and you can measure the accuracy of sensor. However, to measure the precision, you have to repeat the experiment multiple times and get multiple numbers of output and see how close they are confined. For a measurement to be accurate, it should be precise. However, the measurement can be precise without being accurate. Means the accurate measurement is the measurement when it is precise and accurate. However, a measurement can be precise to certain other value which is different than the true value. So, means it may not be accurate. Let us take an example of some bullets we fire. Let us say we fire 5 bullets from a gun, and one knows the exact number of bullets fired, but multiple attempts are made to obtain the precise result. The bullets hitting the bird's eye are precise, and those hitting close to the bird's eye are accurate. So, this is the goal. So, let us say we have this as a goal. We want to hit on this, which is the true value of measurement. We are hitting the bullets, and bullets are not hitting true value. but they are hitting somewhere here, here, which is different than true value. It means this is not accurate. However, if we see all these marks, they are not even confined to a, they are not confined very close to each other. It means this is not even precise. However, this case, all these hit marks, they are very much in a very close range, though they are not at the true value. It means this is precise. Precise means the output is very much confined, but not accurate, which is not equal to the true value of measurement. In this case, if we see the third case, when we have some hit marks are there on the true value, it means the measurement is accurate, but it is not precise again, because we see there is a distribution of these hitting marks. This case, case number 4, where we have all these marks are right at the true value, which means the measurement is accurate, and all the output or all the marks are very much confined to each other. It means this is precise as well. So, this is precise and accurate. So, this is the desired property of a sensor or a transducer. It need to be accurate and it need to be precise. So, this is an example of a case where the system is precise, but it is not accurate. Let us talk about a refrigerator which has a thermometer inside. It measures the temperature and displays out the reading, and we have taken 10 readings, which is 39.1, 39.4, 39.5 and so on, 39.1. All these values we have taken from this sensor. However, the actual temperature inside the refrigerator is 37. So, we can see all the output readings, these are all the output of a sensor, these are all confined to 39 range, 39.1, 39.4, they are very much close to each other. It means this is precise, the sensor which is used in the refrigerator is precise, but it is not very accurate, because the difference between the actual and the measured value is 2 degree, which is 39, let us say 39.0 minus 37. So, it is around 2 degree centigrade is the error which is produced by the measurement of sensor. So, this case is we have precise sensor, but which is not accurate sensor. This is another example of accuracy and precision. So, there are, let us say, 2 sets of data from measurement on 2 different transducers, let us say set A and set B. Set A measurement is 32.56, 32.55 and so on. Set B is 15.38, 15.37, and we need to find out which one is more precise. So, we subtract the lowest data point from the highest one. So, for set A we have 32.56 minus 32.48, which is 0.08, and for set B we have 15.38 minus 15.32, which is 0.6. So, this difference, it shows the range of output. This is the maximum minus minimum. So, this shows the complete range of output, how much the data has taken up. The higher the range of output, less precise the sensor is. It means the sample B or the set B has the lowest range, and so is the more precise. So, the transducer 2 or transducer B is more precise compared to A. Next static characteristic is resolution. So, the resolution is defined as the smallest increment change in the output which can produce a detectable output of the sensor. This is often expressed as percentage of measured range. So, the formula of resolution is R max as a percentage equal to 100 into delta x m divided by mr. How do we calculate is mr or the measured range is equal to x max minus x min, which is the maximum value of x minus the minimum value of x, and for a detectable output delta y, if the minimum change required is delta x, then R max is 100 into delta x m divided by mr. Let us take an example for this resolution measurement. We have a measurement system which can take measurement across a plus minus 10 volt range. It means that the range is plus minus 10 volt, this is 0, this is 10 volt and this is minus 10 volt. And this measurement is being done using a 16-bit A to D converter, 16-bit analog to digital converter. So, the number of levels we will have in this A to D converter will be 2 to the power 16. These will be the number of levels produced by A to D converter. So, 2 to the power 6 equal to 65,536. These will be the number of levels produced by A to D converter, and how much this will correspond to in the voltage? Minus 10 to plus 10 means 20 volt. This full range is 20 volt minus 10 to 10. So, the resolution of this system will be this 20 volt divided by 2 to the power 16, which comes out to be around 305 microvolt. So, the resolution of this complete system using this 16-bit A to D converter will be 305 microvolt. This much will be the output generated by this A to D converter. Next characteristic is the threshold. So, the threshold is at the 0 value condition of the measurand, the input quantity is at its 0 level. How much the smallest input change that produces a detectable output is called the threshold. For example, we have a MOSFET transistor, the input is 0, the gate voltage let us say is 0. How much gate voltage we need to apply so that the MOSFET turns on? So, that is called the threshold voltage of a MOSFET. Another parameter is sensitivity, which is very important for sensors. The sensitivity is the ratio of incremental output to incremental input. So, we can write S equal to delta Y, which is the output, divided by delta X, which is the input. So, this is output divided by input. Usually, we express it in normalized form. So, we can write delta Y upon delta X divided by Y by X. How much is the actual the base value of output and input? We normalize the sensitivity using their base values. In other words, the sensitivity is for a unit change in the input, how much output is being produced by the sensor. So, the sensitivity is the term which we want to have more and more. For a unit input, if the sensor can produce more output, that will be good, or the sensitivity will be very high. If sensitivity or the out level changes with time, temperature and or other parameters without any change in the input level, that is called drift in the system. Sometime the output of a sensor changes with other parameters as well, for example, temperature, and that is called a drift, and which leads to, most of the time, which leads to the instability in the system. The example is, let us consider a pressure sensor that has a measurement range of 0 to 100 psi and an output range of 0 to 5 volt. Its sensitivity is 0.05. volt per psi. The sensitivity of an instrument says nothing about the quality of an instrument. This is typically established by the instrument's accuracy and precision. Next parameter is selectivity. The output of a sensor, let us say we have a sensor which we designed for a particular parameter. This sensor is not only sensitive to only that parameter, but it is sensitive to multiple other parameters. For example, temperature. If the temperature changes, the output of this sensor also going to be changed. So, the output of a sensor may change when afflicted by environmental parameters or even some other variables, and this may appear as an unwanted signal. So, the sensor is then said to be non-selective. When the sensor starts sensing other parameters as well, then this sensor is called a non-selective sensor, and we can write this partial sensitivity to other parameters as SJK, where K is some other input and J is some other output, and SJK equal to delta YK divided by delta XJ, means change in input X produces a change in the output Y, where the output Y may not be a desired output from delta X. And a selectivity matrix would be obtained SJK and the jth entry, and obviously an ideally selective system will have only diagonal entries. So, this we will see in the next example. So, for example, we have a gas sensor and we make this gas sensor to detect oxygen, carbon dioxide, CO, NH3, VO and other VOCs. So, the input quantities are these 5, and based on that the output will be generated. So, for example, if we flow the oxygen in this sensor, oxygen output according to oxygen will be produced. If we flow CO in the system, the CO output corresponding to CO will be produced. However, the sensors, they have partial sensitivity to others as well. For example, we flow oxygen in the system, there will be a output generated by O2 according to O2, but there will be partial sensitivity to CO as well, which should not be there. Similarly, if we let us say we flow NH3 in the system, so NH3 should be detected, but along with this VOC is also going to be detected. So, this is undesired, which is because of the non-selectivity of the sensor. If a sensor is very selective, then we will have only the diagonal element, means the oxygen will produce output according to oxygen here, CO2 will produce output according to CO2 only, CO will produce output to CO only, and NH3 to NH3 and VOC to VOC. So, we will have only these diagonal elements in the selectivity matrix for a selective sensor. Next parameter is non-linearity. When the output of a system deviates from a perfectly linear output, then it is called a non-linear system, and this non-linearity can be specified in two different ways. First is, let us say we have in this graph we have this output produced. So, we can fit a straight line in this output, and the difference between this fitted line and the actual data, this is the error produced by measurement. So, this is one expression of non-linearity where we fit the data, fit a line in the data and express the error. Second is, we just join the first point and the last point using a straight line, and we measure this error between this fitted line and the actual data. So, this is based on joining the end points of the scale, and the maximum non-linearity in the first method this is always lesser than the second method. So, this method will have lesser error compared to this method. A consequence of nonlinearity is distortion. So, when the output of a sensor deviates from a straight line output, then it produces distortion, which is defined as the deviation from an expected output. So, let us understand what is nonlinearity. So, consider a linear system where we have this is a completely linear system and we apply two frequencies to its input, let us say frequency 1 f1 and frequency 2 which is f2. We are talking here in terms of frequency domain and we have this frequency spectrum f1 and f2, these two frequency we apply at the input. This linear system will only produce output at these two frequencies. It means the output will be amplified, the level here will be different. Let us say at input it is A and the output it will be A1, but the frequencies will be same f1 and f2 only. So, no harmonic generation in linear system. However, if we have a non-linear system here, we apply only two frequencies, but because of the non-linearity the system will generate harmonics. Harmonics are integer multiples of the input frequencies. So, at the output we get f1 and f2 and we get harmonics as well. So, we get f1 and f2 and the second order harmonics will be f1 plus f2 and f2 minus f1. These are the second order where we have two terms added or subtracted together, and this f2 plus f1 will be somewhere here and f2 minus f1 will be here and f2 plus f1 will be somewhere here. Third order harmonic will be where three terms are involved. Here two terms of f1 minus one term of f2 and two terms of f2 minus one terms of f1. So, this is third order harmonic which appears somewhere here. So, this is a non-linear system where the system generates harmonics of the input frequencies and these harmonics are generated due to the non-linearity of the system. These type of non-linearity or these harmonic generations, these are very important for high frequency applications. Next characteristic is hysteresis. So, hysteresis is the difference in the output of the sensor for a given input x when x reaches its value in upscale and downscale direction. Means we have an input range, let us say from x min to x max. When we apply from x min to x max, the output follows this path, but when we come back from x max to x min, the output follows a different path. The output does not go to the same path, it follows a different path while coming back, and for going up this is the path. So, these two paths are different. Ideally it should be same, but if the system has hysteresis or the memory effect we call it, then these outputs are different and there is exist an area in between. So, this is called hysteresis in the system. This is the case of analog, where we have in analog measurement hysteresis look like this. However, in the digital case it look like this. When input is changed from low to high, it follows this path, but when coming back from high to low value, this follows different path. So, this is a digital case where a Schmitt trigger produce this kind of hysteresis loop. Next parameter is the impedance. So, this input output impedance of the sensor or a transducer is the characteristic which need to be considered when we start connecting more than one systems in cascade. Let us say we have one system and we want to connect it to the other system. That time we need to take care of the how much is the input impedance and output impedance of these systems, and these causes significant restrictions in interfacing these blocks. For example, here in this case we have this voltage source which is 100 millivolt in magnitude, and it has a, let us say, internal impedance of 1 ohm. And we want to connect it to an amplifier which is shown here. This is amplifier. This amplifier has an input impedance of, let us say, 100 ohm. In isolation condition, this voltage source will produce a 100 millivolt output here when it is in isolation, it is not connected to any other block. But as soon as we connect this voltage source to an amplifier which is 100 ohm in input impedance, the voltage at the input will not be 100 millivolt. This will be distributed between this Zs and Z1. The net voltage will not be 100 millivolt now, it will be approximately 100 divided by 100 plus 1 into 100 millivolt. This is your Zin divided by Zin plus Zs into 100. So, this 100 millivolt will be divided using resistor divider across this path, and this voltage is now lesser than 100 millivolt because this quantity is lesser than 1. So, it will be typically some 99 millivolt or so. So, because of the interconnection of these two blocks, now the output produced by this voltage source is reduced as soon as we connect these blocks together. So, these input and output impedance need to be taken care of. If we have a very less impedance at the input of this amplifier, this voltage is further going to be reduced and accordingly our system gain will be limited. So, these input and output impedances are some static characteristic which need to be considered. Next is isolation and grounding. So, isolation is necessary to eliminate or at least reduce undesired electrical, magnetic or electromagnetic and mechanical coupling. So, when we have these sensors and we connect it to some electronics, then that electronics may be working at different voltage and this sensor may be working at different voltage, for example 5 volt, but the processing unit which is, let us say, computer or some electronics which is working at 12 volt. So, this sensor should not be exposed to this 12 volt because sensor is at 5 volt. If 12 volt comes in, the sensor can be damaged. So, there should be an isolation between this sensor and electronics. However, the data should flow from sensor to electronics. It means the AC signal, the data should flow, but the DC voltage should be blocked. So, we use some kind of decoupling capacitors between these two blocks so that the DC voltage are isolated, however, the AC signal can flow. Similarly, grounding is also necessary to establish a common node between these different parts of the system with respect to which the potential of any point in the system remains constant. We need to have a common ground with reference to that we define all the voltages of other nodes. So, these are some static characteristics of the sensors which we use for characterization of these sensors. These are some other examples. For example, the length of a rectangular box is 1.2 meter, but if it was measured with a tape and the length was measured at 1.22, what is the accuracy of the system? So, similar kind of experiment, similar kind of example we considered earlier as well. This is the actual value or the true value x t, and 1.22, this is the x m, and so we know the formula, error equal to x m minus x t divided by x t into 100. So, we put the values and we get the results. Around 1.67% is the error in this measurement. Hence, the accuracy is 100 minus 1.67, which is 98.33%. Another example is, let us say we have a measuring tape and it can measure with an accuracy of 99.8% only. What is the possible range of length which can be obtained by using this measurement tape to measure a cloth of length 2 meter? So, this 2 meter length is the value of x t, and we are given accuracy which is 99.8%. So, the error will be 100 minus 99.8%, which is 0.2%. Now, the new measurement or the measured value using this measuring tape will be actual value 2 meter plus minus the error, which is 2 plus minus 0.004. So, the maximum value of measurement will be 2.004 and the minimum value will be 2 meter minus 0.004, which is 1.996. So, this is all we have for today. Thank you.